Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electrical machines and basic concepts related to it. So far we have discussed about in the previous videos about magnetic materials, classifying it to three categories: diamagnetic, paramagnetic and ferromagnetic, discussing it separately. So in this video we are going to discuss about another important concept related to magnetic materials, which affects their design characteristics. This is called as hysteresis. So we know that ferromagnetic material and paramagnetic material, they exhibit magnetic behavior, okay, in the direction of the magnetic field, attractive type magnetic characteristics. Paramagnetic shows weak attractive characteristics, ferromagnetic shows strong magnetic characteristics. And we discussed in the previous video that ferromagnetism is just extreme form of paramagnetism. So when a ferromagnetic material is subjected to a magnetic field and that magnetic field is removed, it retains the magnetic behavior. It does not lose its magnetic behavior. Whereas in paramagnetism, paramagnetic materials, they lose their magnetic characteristics as soon as the external field is removed. Hysteresis is all about that residual magnetism. So hysteresis is basically the phenomena that when a ferromagnetic substance or a ferromagnetic material is subjected to a cycle of magnetization and it is magnetized in one particular direction and then the direction is reversed, it retains some of the magnetic characteristics, which is expressed by the magnetic flux density B, and the magnetic force by which it is magnetized, that is capital H. So this lagging property of magnetic flux density, or the residual magnetism which the ferromagnetic material shows, that is called as hysteresis. So this is just the definition. Let us now try to understand what it means. So there are two important parameters that are involved to understand the hysteresis curve. So hysteresis is derived from the Greek word hysterin, which means to lag behind. So there are two parameters which are important here. First is the magnetic flux density and second is the magnetizing force or magnetic intensity. So magnetic flux density is basically the number of magnetic lines of force passing through a area, passing per unit area, surface area. So if we have a surface area placed at an angle theta, the area vector makes an angle theta with the magnetic lines of force, then the magnetic flux phi is equal to BA cos theta when theta is equal to 0. In that case, magnetic flux density is simply flux per unit area. So it has the unit of Tesla or Weber per meter square, which we have already discussed. So that's why I'm not going into detail. Sorry. Then we have is the magnetizing force or magnetic intensity. So it is basically the number of ampere turns of current flowing per unit length of a material. So if we have a material with n turns of coil wound over it and a current I flows through it, then the magnetic force or magnetic intensity is given by the product of the number of turns and the current flowing through it. Okay, so these are the two parameters involved in hysteresis. So now, in order to understand hysteresis, what is this lagging behavior or residual magnetism? Let us say we take a material, ferromagnetic material, in this case iron core toroid. So it looks something like this, kind of a circular shape, you know. uh, then we have number of turns of coil wound over it, and we have current I flowing through it. So total number of turns here is capital N, and L is the length of the toroid. Okay, this is not capital I, this is actually N. So we have a iron core toroid with N turns of coil, and L is the length of the toroid coil. So in that case, the magnetizing force is per unit length we have to calculate. It's not simply Ni, but Ni by L, magnetizing force per unit length of the coil. So this value of H, as you can see, it can be altered by changing the current, because the number of turns is fixed, the length of the coil is fixed. So this iron core toroid is subjected to a magnetization cycle by changing the magnetic intensity or magnetic force H, Ni by L, that by changing the current. So this BH curve, or the plot between the magnetic flux density through the coil and the magnetic force which is given to it, the magnetization force that is given to it, that loop or that curve is called as hysteresis curve or hysteresis loop. So it looks something like this. Okay, so we will start from this point O, where the magnetic force is 0, nothing is given, no magnetic field is applied, and the resultant magnetic flux density in the coil is also 0. Now let's say H is increased. It is increased in this direction, and as a result the magnetic flux density takes this dotted path. Okay, it takes this dotted path and it reaches up to this point A, this point. Okay, this point A. Then okay, yes, this point A it reaches. Then at this point, this is the magnetic force which is applied, corresponding to the maximum magnetic flux. Okay, this, the corresponding to this maximum magnetic flux, this. Okay, now when this magnetic flux corresponding to the maximum is there at point A, from this point, when the magnetic intensity or magnetic force is reduced, H is reduced, the thing here which is interesting is that it does not take this path AO. Okay, it does not follow this path AO which took originally, but it takes the path AB, okay, instead of AO. Starting from O, it reached this point A by taking this OA path, but when the magnetic flux was reduced from here, okay, when it was reduced, instead of taking the path AO, it took path AB. So another interesting point here is that when at this point the magnetic force is 0, the magnetic flux density in the material is not 0. It has this value BR. This value BR, which means some amount of residual magnetism is there. That is called as residual magnetic flux density, and that is called as remanence or retentivity. Okay, that is called as remanence or retentivity. the residual magnetism, the residual magnetic flux density, okay, at this point P. Now if we want to make the value of magnetic flux density in the material 0, we have to apply the magnetic force in the reverse direction, in the opposite direction, by reversing the direction of current. So in that case, the reverse magnetic force that we have to apply to make the magnetic flux density in the material 0, that is this point C, okay, this where the magnetic flux is 0, the magnetic flux density B is equal to 0 at this point. Now this reverse magnetic force which has to be applied in the reverse direction to make the magnetic flux density equal to 0, that is called as coercive force, okay, it is called as coercive force or coercivity. This to completely wipe out the residual magnetism, or it is called as coercivity or coercive force, to make the magnetic flux density in the material 0. Then when the magnetic force H is increased further in the reverse direction, the material, it acquires magnetic flux density in the negative direction and attains a saturation value minus B max, which is equal in magnitude but opposite in direction at this point D, okay. Then at this point again, when H is further increased in the right side, again the polarity of the direction of current is changed and the magnetic field, external magnetic field polarity is reversed. Again at this point where H is again 0, it has some residual magnetism in the opposite direction, negative, which is minus Br, negative residual magnetism at point E. Then further H is when H is completely magnetic flux density which is 0 here, and the corresponding H value here is F, which is the coercive force in the positive direction, coercive force in the positive direction, okay. It is the amount of magnetic flux density in the positive direction which is required to make the magnetic flux density 0. So this lagging, this lagging of B and H curve, this residual magnetism which it exhibits, even though the coercive force or the magnetic force is 0, that is called as hysteresis curve, or the phenomena or of hysteresis. So it is very important for the design characteristics of various electrical machines, be it permanent magnets, electromagnets, design of transformer cores, or in case of generators, motors. So this property of hysteresis comes into play. So this total loop starting from O to A, then A, B, C, D, E, F, that is called as the hysteresis loop. This ABCD plot, ABCDEFA, that is called as the hysteresis loop, okay. So this is the basic concept related to hysteresis. So we have discussed about hysteresis, the basic concept related to it. So there is another important aspect related to hysteresis, which is hysteresis loss. So we know that when a ferromagnetic material is subjected to external magnetic field, the main reason for the strong magnetic behavior in ferromagnetic materials is the domains or groups of magnetic dipole moments, okay. So that is the reason why ferromagnetic materials have strong magnetic dipole moments and strong magnetic behavior. Now, when the ferromagnetic material is subjected to magnetic force in both the positive and negative direction, plus H and minus H, a whole cycle, they are magnetized in one direction and then in the opposite direction. Okay, so the domains or the clusters or groups of magnetic dipole moments, first they align in one direction, then in the opposite direction. So what happens is that these domains, their natural tendency is to offer resistance to being rotated or to being turned, first in one direction, then in the other direction, when the direction of the magnetic field is changed. So extra energy has to be supplied, that is more magnetic force has to be supplied to overcome this opposition. This extra energy causes loss in the form of heat, and that is called as hysteresis loss. The energy or the extra energy applied to overcome the opposition offered by the domains in being rotated or turned from one direction to the other when the direction of the magnetic field, sorry, this is not electric field, this is magnetic field, by mistake I have written electric field, this is magnetic field. So that is the hysteresis loss. So hysteresis loss is present in all electrical machines which have iron parts and which are subjected to cycles of magnetization, and the obvious effect of hysteresis loss is the rise in the temperature of the machine. So there are various applications of this hysteresis curve or loop. The shape and size of the hysteresis loop largely depends on the nature of the material, nature of the ferromagnetic material, and it depends on various other characteristics such as important properties such as susceptibility, then permeability, flux density, and the choice of a particular ferromagnetic material for a particular application in electrical machines. It depends on the shape and size of hysteresis loop. So here some important points that are worth noting. The area of the hysteresis loop, it gives us information about the hysteresis loss. More the area, more the hysteresis loss, less the area, less the hysteresis loss. So obviously materials with smaller hysteresis curve area are preferred. Then retentivity or remanence gives us information about the residual magnetism. So higher the retentivity or remanence, higher the residual magnetism. So materials with higher retentivity are strongly magnetized and they are preferred more. Then coercive force, we know, is the magnetic force that has to be applied in the opposite direction to remove the residual magnetism, to bring magnetic flux density to zero. So materials with higher coercivity will require more magnetic force to destroy their residual magnetism. So depending upon various characteristics, various features required in a particular electrical machine, different materials are preferred. So these are some of the important concepts related to hysteresis, and we have discussed them. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.